So if I'm 1 meter away, given my constant is 0, then my electric potential at this spot, well, plug and chug, that's 9 times 10 to the 9th, times 3 times 10 to the negative 9th. Wow, what a coincidence. Divided by 1, and I get 27. So my potential there is 27 volts. And let's see if I can clean that up a little bit, because that's looking really cluttered. So I have my 3 nanocoulomb. I got my 3 nanocoulomb charge here. If I am 1 meter away, my electric potential is 27 volts. If I'm 2 meters away, so I add another meter, what is my potential?
27 over 2.
Add on another meter, if I'm another meter away.
13.5 over 2.
Would it be 9?
Be 9.
I understand.
Yeah, that's just 9. Now, all of these are electric potentials. If I have a 12 volt battery, so this V right here stands for volts. This V right here stands for electric potential. This U right here stands for electric potential energy. Please keep track of those. This is another situation where, or the first time, I think I made an allusion to it in the first semester course, but if I have V is equal to 2V, in math class V would be 0, but in physics, this is a variable and that's a unit. The math people just don't know what they're doing, right? You know what I'm saying?
No.
Is there like a notation difference, or do they look identical?
They look like they're both capital V's.
You could
Yeah.
have at least made one small.
Yeah, like won't that be lowercase? Is that not an option?
That's just crazy. No. Lowercase v, if this is lowercase, then we're talking,
Velocity.
yeah, well, speed. Put a vector symbol over it, it's velocity. But in context of this course, lowercase v would be alternating voltage, the voltage for alternating current.
Oh, okay.
Can we put, like, make it in italics or something?
Whatever you need to do, like when I'm typing it out, no, it's gonna look, those V's will look the same. Here's the key difference. The unit comes after a number. That's the key difference.
You don't do like a dotted line with like a sine wave above it for alternating current?
Alternating current, you tend to use the lowercase to indicate that it's changing,
Okay.
as opposed to direct current where it pretty much is.
Because like the simples that I've seen, they've used a dotted line for direct current with a straight line over it, whatever the V is, and then for alternating current, they've used just a dotted line with a little sine wave over it.
I mean, over this.
Yeah,
the
over
symbol
the
there?
V for
Okay.
voltage, but
I do not recall having seen that, but.
if you look at a voltmeter or a multimeter.
Oh,
So I was gonna say
okay.
multimeter.
Multimeter just has a V on it. Well, we can check what we have.
What are the units of a volt?
Volt is a unit.
Like,
Voltaires.
like, you know how there's a Newton is something meters squared over second
Oh,
squared?
what is it, SI units?
Yes.
Let's see. Let's see, that's amperes, that's ohms. The volt is an ampere ohm. And doesn't get us down to, To get from potential energy to electric potential, the electric potential energy to electric potential you divide by a charge. So if this is joules, this would be joules per coulomb.
Okay.
And a joule is a kilogram meter squared per second squared over coulomb. Coulomb was not the official SI unit, or, yeah, I mean, it's a derived unit. Ampere is the official, or was the official, and that's a Coulomb per second, so Coulomb ampere second. So this would be a kilogram meter squared per ampere second cubed. Yeah. Which means second cubed is a kilogram meter squared over ampere volts. Which means that the cubed root of kilogram meter squared over ampere volts is a unit of time.
It's a unit of time.
That's a second. There's 60 of those in a minute.
I will meet you in cubed root kilogram meter squared. Volts.
We'll start using that.
Please do.
Let's make it.
And this is a segue, I might have talked about it before, but not everyone's had me before. One of my all-time favorite questions, horrible execution, but still I think a great question. It was 15 multiple choices, 15 choices of a multiple choice. And the question was, which of the following are units of time? And I think all but one were units of time. And so it was things like this, and what I wasn't thinking about was how long it takes to do each one to figure out which one goes back to a second. But the sad thing was, besides my not recognizing how people would go about tackling that problem, was the number of people who did not put down the choice that was the letter S.
People didn't put down S.
That was like the middle choice, right there in the middle. I think at that point, they were so psychologically beaten down that.
It's just too easy to be true.
Yeah.
There could have been that too.
They're like,
It's a
it must be
trick
distance, but I don't know.
It must be centimeters. S.
Now,
Speed.
if ever you see a problem and there's a little bit of an icon there with a gift, that means it probably is as easy as you're thinking it is. Occasionally, I will put a gift icon next to a problem.
I had to really think about on our last one.
Yeah.
The gift one, I was sitting there like,
I was like, what does this mean?
I'm telling you, so, or should I have just made the other people suffer?
my physics is just psychological warfare.
But there are times I would agree with you. All right. However, do recognize, back to this, that these are the electric potentials, assuming that it is zero an infinite distance away. You notice it's getting smaller as we go. It makes sense that it would eventually go to zero. If I changed where my electric potential is zero, all of these numbers would change. I could make this zero because I said so, which would then change the others. But how much would the others change? If this suddenly became 0 volts, what would that one be?
Negative 13.5 volts.
And that one?
Negative.
27?
No, that's like negative 22.5.
No, negative
No.
8. Or yeah, negative 18 volts.
Negative 18. Just subtract 27 from everything.
No.
This negative volts.
What is it? All right, so what really matters here in terms of practical application, and I think this will address your question, is the difference. The difference from here to here is the same as the difference from here to here. And going the other, so it's negative 13.5 if I go that way, positive 13.5 if I go that way. That is really what matters.
Oh, so it's just the magnitude?
Magnitude of the difference. Well, no, I should just say it's the difference. It does matter which way you're going.
Okay.
Because if I have a battery here, this is at a higher potential than that is. So the current will flow that way. That's the direction of current flow. If I flip the battery around, the current's gonna flow the other direction. So which way you go matters. This is stuff that we will get into. So what really matters is the difference. That difference there, that is voltage. So voltage is the same thing as electric potential difference. And also note, we are at the place where if I ask for the potential, I am not talking about energy. In the first semester course, we could get away with, hey, what's the potential of the situation? Because there was only potential energy. Now we have two things with the word potential in it. Potential is a reference to electric potential. If I want the energy, I need to specify energy.
So is voltage change in capital V?
Yes. So that's why down here, I wrote delta V. This is the symbol for voltage. Now, I don't think CATS does it. Some textbooks do, and I never keep track of, I have difficulty keeping track of which ones do it and which ones don't. Some textbooks will drop the delta. Here's the thinking. I know that voltage is equals V final minus V initial. So I'm going from one place to another, whatever my final potential is minus the initial potential. Since where zero is arbitrary, why not just make that zero? So now this is equal to Vf minus that. And since I have only one V over here, then well, why not just write it as V? So some textbooks go through this logic without really explaining it. They'll use electric potential and voltage interchangeably. This is the thought process behind that. I try not to do that. So if you have a formula, if I give you a formula with just a plain old V in it without a delta in front of it, I am talking about electric potential. If I want voltage, throw the delta in front.
The volts is the unit, and then voltage is the change in volts.
Change in electric potential, which has units of volts.
Okay.
Don't worry, the most confusing thing I think in this course are the 6 different mu's.
Oh, God.
Thanks.
But I have a video on don't confuse these mu's, so that should clear everything up, no doubt. Okay, in today's lab, you're gonna have a sheet here with a positive and negative nodes. You're gonna hook up a power supply to it, and so I will have the electric field will basically flow like this, from away from positive towards negative. Etc. If I'm trying to find potential, because I can't actually measure electric field, we don't have anything that will measure the electric field. We have to sort of do it through the back door. What we're going to do is we're going to measure the potential difference between the negative charge and some other place. So I'll have a probe connected to this, and then I'll figure out what the potential is at this point right here. I'll find another point which has the exact same potential difference between here and there. It's a scalar, so direction doesn't matter. And then, and so on. I'll find 5 points which have all the same electric potential. Now, in theory, there's an infinite number of points, but it's just sort of connect, smooth it out. It's not a connected out exercise. The electric potential lines were not going to look like that. Smooth it out. All the places on this line right here are believed to be the same electric potential difference between it and the negative charge. This is known as an equipotential line. And let's see if I can actually write it so it's more visible. How about green? Now, there is a characteristic between the equipotential lines and the electric field. And we'll just look at a quick example here. If I have a positive charge, I know my formula for electric potential is KQ over R. So, well, Q is that charge right there, K is a constant. So for this charge right here, anything that's the same distance away will have the exact same potential. Would be an equipotential line, assuming I drew that so that that's in the center of a circle. A different equipotential line will look like that, would be farther out, or should be one there. These are all supposed to be circles. My electric field goes away, and you know what, we can get fancy here. Ooh, my electric field lines are going away from it. And so if these green lines here, these green circles are concentric around this, and my electric field is radiating outwards, there's a right angle here. And so the equipotential line, is perpendicular to the electric field. So we will find equipotential lines, and then from that, draw the electric field, which I know is going to go from positive to negative. And it will, and then, so you'll just draw it out. Now, suppose in a nice ideal case, it'll be very clear. Matter of fact, on the first page, I think it's on the first page, might be on the second page, I give you what the ideal looks like for this scenario. What is physics lab? What are the chances we're going to get the ideal? You got your positive, you got your negative charge here, and you got an equipotential line that kind of looks like that, and another one that kind of looks like that. Let's say these are your equipotential lines, and now I'm asking you to draw an electric field. I do expect you to obey that. I know it's going from positive towards negative, and it has to cross this at a right angle, so.
A line.
So when I grade this, there's a little squiggle right there. When I grade this, what I do is I do a spot check. I look at your equipotential lines, I look at your electric field lines, and I just sort of run my eyes over it, and if there's any place where the electric field is not perpendicular to your equipotential line, well, there's the deduction. So the electric field lines that you draw an arrow there because it does have a direction. The electric field lines should be based upon your equipotential lines. Questions to hear?
Are you gonna check with like a protractor? Or just,
No,
just,
I'm eyeballing it. There's a certain amount of close enough and a certain amount of that's clearly not the
Okay.
right angle.
We put right angle squares at each line.
There are some times that I'll go, yeah, I'll agree with that, and sometimes I'm gonna go, no, that's just fantasy. They have not been beaten down enough by physics, so let's change that. So I recommend when you're doing this, start out with just a pencil, something that you can erase easily. Now, the warning before we begin this, there's a lab that we've been doing. I did a video on the lab that we've been doing for a couple of years now. This group, is gonna do a different one. As we were moving over to here, I found some what are called overbank boards. And I thought, you know what, this might work better. So what the lab that I'm gonna hand out to you is gonna be a version 1, which means who knows how many mistakes are in it.
Ah.
So if you have questions, don't forget to ask. And I think on that absolutely spectacular note, let's head down to the other room. And I will go grab the labs. The door should be unlocked, so feel free to just
It's the next
walk
room
in.
over?
Pardon?
Is it the next room over?
30, oh, that's right, this is the first time we've actually done a lab in person. 306. The former nanotech room, if that helps.
Okay. Are you wearing the face shields?
Pick through two.
Would you like a face shield? Okay. The mask.
I have understanding of the plight, so.